Welcome back everyone. In this lecture I continue to provide some applications of Lagrange's theorem. Again we will see some applications in number theory. So let us look at this particular multiplicity group. Okay, so let us take Z modulo NZ and then all invertible elements in this group. Okay, so recall, so this is actually parameterized by, okay, you can collect all this A plus NZ where A is coming from between 1 to n and the GCD of A and n, that must be 1. Okay. So, those elements, so those numbers that are relatively prime to n. So, those, that is the parameterizing set for this Z modulo NZ cross. And when you do the multiplication, okay, how the multiplication is defined, A plus NZ into B plus NZ. So, this is exactly AB plus NZ. Okay. So, the multiplication is inherited from the top group, so which has multiplication Z. Sorry, yeah. So, there is a ring Z, you are getting that multiplication from the ring Z. Okay. So, we already seen that the number of elements or the order, okay, of Z modulo NZ cross. So, this is going to be exactly phi of n. So, this is the Euler phi function, okay, Euler phi function, and we know that how to compute this. Okay. So, I have already told you how to compute all this. So, now if we take this group and then apply our Lagrange's theorem, okay, for example, I can start with any integer. Okay. You take any integer A, again you can assume it to be non-zero because we want to call it relatively prime with n. So, let us assume that this A and n, they are relatively prime. Okay. So, in particularly I can consider this as an element inside your group Z modulo NZ cross. Okay. So, this is the group. Okay. In particular, I can take A plus NZ. So, this is an element inside Z modulo NZ cross. So, this is the complete set of elements, those non-zero integers which has GCD A comma n equal to 1. So, those are all the elements of the Z modulo NZ cross. Okay. And here this is the parameterizing set. So, now this element, if you call it x, then it is clear that the order of x, okay, should divide order of this group Z modulo NZ cross. So, but what it is exactly phi of n. Okay. So, but what does it mean? So, x power phi of n must be identity inside this group G. Okay. So, let us rewrite this. So, if you rewrite this, what is the meaning of x power phi of n equal to identity? So, identity is nothing but 1 plus NZ. Okay. So, that is what identity inside Z modulo NZ cross. And what is the meaning of x power phi n is being identity. So, that means if you take A and then raise it power phi of n, that must be congruent to 1 modulo n. Okay. So, that is the meaning. So, that means you can see that this A power phi of n must be congruent to 1 modulo n. Okay. So, this is an immediate corollary of our Lagrange's theorem, and this is called actually Euler's theorem in the literature, and all the theorem that we know in elementary number theory can be reproved here using Lagrange's theorem. So, many of the results are coming for free here. Okay. So, this is actually a very powerful theorem. Okay. Let us see one example, okay, and then I will demonstrate how powerful is this Euler's theorem. Okay. Uh, so let us say we want to compute the last two digits of this 3 power 100. Okay. So what it is? It is 3 power 3 and then power 100. So we want to compute last two digits of this 3 power 100. So that is our question. Okay. So how do we compute last two digits? Okay. You write it in first of all decimal expansion. So that means this 3 power 100, okay, whatever way you write like 1 plus some a naught, okay, let us call it a naught times 1, a1 times 10 and then a2 times 10 square plus etc. So this a naught, a1, a2 they are all coming from 1 to 9, sorry 0 to 0, 1 to 9. So that is how you get the decimal expansion. And if you are interested in computing only the last two digits, then you have to go modulo 10 square, because everything else will be 10 cube and so on. Okay. So that means if I compute 3 power 100 congruent to whatever modulo 100, so then this is what gives us last two digits of this 3 power 100. But how one can compute this? That is the question. But note that Euler's theorem says a power phi of 100 is congruent to 1 modulo 100. Okay. So this is what Euler's theorem says. So if you go back to the thing, you can see that a power phi n is congruent to 1 modulo phi n. Okay. So in particularly a power phi 100 is congruent to 1 modulo 100. So if I compute this 3 power 100, if it is congruent to some x modulo, let us say this phi of 100, so then that actually helps us to compute things, because if 3 power 100 is congruent to x modulo 100, then what we get? We get 3 power 100 is equal to x plus some k times phi of 100. Okay. Then if you compute 3 power 100, so that will be equal to 3 power x, 3 power k times phi of 100. Okay. But you already know that a power any of phi of 100 is congruent to 1. So then if you go modulo 100, 3 power 100 will be congruent to 3 power x, 3 power phi of 100 power 1, okay, and then modulo 100, okay, sorry, power k. But note that 3 power phi of 100, that is congruent to 1 modulo 100. Okay. So that means this term, this entire term will become congruent to 1 modulo 100. So that will tell you that 3 power 100 will be congruent to 3 power x modulo 100. Okay. So that means if you compute what is this x, that is going to tell you what is this. But what is phi of 100? Phi of 100 is nothing but 10 times 10 square, which is 2 square into 5 square, and phi of 100 is phi of 2 square, phi of 5 square, which is 2 square minus 2 times 5 square minus 2, 5 square minus 5. So that is nothing but this is 2 times this is 5 square minus 5, 20, which is 40. Okay. So then you want to compute 3 power 100 congruent to x modulo 40, and you can easily see that 3 power 4 is nothing but 81, which is 9 into 9, 81. So 3 power 4 is congruent to 1 modulo 40. Okay. So that tells you that 3 power 100, okay, is congruent to 3 power 4 power 25, which is congruent to 1 power 25 modulo 40. So then 1 is actually your x. So x is actually 1. So if you substitute back in this, you can see that 3 power 100 is congruent to 3 modulo 100. So that means 0 and 3, okay, because this is 0, 3. These are the last 2 digits of 3 power 100. Okay. So one can do such computation very easily because of Euler's theorem. Okay, and Euler's theorem is a very simple consequence of Lagrange's theorem when you apply it for this particular group. So we can also get some more applications. Okay, let us look at one particular group as follows. Okay, so let us take your group to be z modulo p power n minus 1 z, okay, where n is a positive integer and then p is a prime number. Okay, consider this z modulo p power n minus 1 z and then look at the multiplicity. So all the examples that we use are multiplicity group. Okay, that is very important, modulo that whatever corresponding integer. So now you can easily see that if you consider this p plus this pn minus 1 z, this element, okay, which we call it p bar. So inside this G, okay, then order of this p bar. So this has to be n. Why that is the case? Note that p power n minus 1. So p power n can be written as p power n minus 1 plus 1. So that says that p power n is congruent to 1 modulo p power n minus 1. Okay, that means order of this p bar divides n, okay, or order of p bar is less than or equal to n. Now suppose if you denote this order of p bar equal to k, then this p power k must be congruent to 1 modulo n, sorry, 1 modulo p power n minus 1. So this already tells this k is less than or equal to n. Okay, now we have such equation. What we get from this equation? We can see that p power n minus 1 divides p power k minus 1. And it is easy to see this will definitely imply n is less than or equal to k. Okay. Now you already have k less than or equal to n. Here you have n less than or equal to k. So that would imply that k is equal to n. If k is equal to n, that means the order of p bar is nothing but n. Okay, what is the meaning of order being n? Okay, so order of any element p bar must divide order of the group, but order of the group is what? Z modulo pn minus 1 z cross. Okay, so the order of that is nothing but the Euler phi function applied on pn minus 1. Okay, but order of p bar is n. So that means we get this immediate corollary, n divides phi of pn minus 1. So such an interesting fact is immediate from Lagrange's theorem. So for any natural number n and any prime p, n always divides phi of p power n minus 1. So note that it is not that easy to compute what is this pn minus 1, p power n minus 1, because even though it looks like some x power n minus 1 formula, all you can do is you can use this x power n minus 1 and then compute x minus 1 into the remaining term. But how do you factorize this element, or even this element is not that easy, clear, okay, because this x minus 1 is going to be just p minus 1, okay. P minus 1, even though p is prime, p minus 1 can be highly reducible. So the factorization of this may not be that easy to do, but still we are able to say that given any n must divide this phi of p power n minus 1, okay, which is very interesting fact from elementary number theory, which we can prove using our group theory ideas. Okay, so as I already noticed or said before, so you have a natural bijection from the left set of all left cosets of H in G and then the set of all right cosets of H in G. Okay, you fix a group G and then a subgroup H, okay, and then from any group, okay, G to G, there is this very nice bijection G, okay, which is given by x goes to x inverse. Okay. So, it is easy to see this map is a bijective map. So, it defines bijection between G to G. Okay. So, such nice bijection what it does. So, if I take this left coset and then apply, let us call this map let us say f, then f of hx xh. So, this is going to be, if you do the computation, you can easily see that this is going to be just h x inverse, okay, because x y inverse is nothing but y inverse x inverse for all x y in G. So, that immediately tells that if you take this left coset, that is mapped to right coset by this inverse map, x goes to x inverse map. So, this is actually very interesting involution map, which actually defines automorphism of G. So, from this observation you can easily see that. I will leave it as exercise. So, this is easy to verify. So, this map, when you restrict to the set of all left cosets of H and G. So, from here to the set of all right cosets of G, right cosets of H in G. Okay. So, this XH is mapped to H in X inverse. So, this defines a natural bijective correspondence. Okay. So, this is also one of the reason that we can only stick with the left cosets. There is no issue with that. Okay. So, now let us go back to our actually our examples, and then we have made some very important observation. Okay. So, let us actually recall what observations that we have made. For example, we took this R2 and then when we went modulo x axis, we actually realized that there is a natural parametrizing set which is y axis that gives bijective correspondence between this R2 modulo x axis and y axis. Okay. So, this is the bijective correspondence. And similarly, when we took this C cross and then when we went modulo S1, so there is a natural bijective correspondence between this and the positive ray R plus, I guess I denoted it by upper plus 0 comma infinity. Similarly, when we took C cross and then went modulo 0 infinity, then we got natural correspondence with S1. So, what is happening here, when you look at this natural parametrizing sets on the right side, they are all groups on their own. Okay. For example, if you take y axis, there is an addition of R2 that can be restricted to this y axis. So, in this y axis is itself is a group. Similarly, if you take this ray 0 infinity, so the multiplication restricted to this will make a group. Similarly, S1 as well. Okay. So, that means these left cosets okay, that we have on the right hand side, somehow they are actually, by identifying them with this natural uh, representatives, so they kind of carry some kind of interesting structure, that is what group structure. Okay. So, this is somewhat motivates us to look for, is there any group structure on the set of all left cosets. Okay. So, you can easily see that here all these examples are all commutative. Okay. So, in case if you are interested in actually putting a group structure on this set of all left cosets G modulo H. So, we have to be little bit careful. Okay. Let me explain what we need to do. So, let us take these examples and then first try to understand what is really happening. So, because when I say the right side has group structure and somewhat that motivates us to define a group structure on the left side. So, we are not looking for some arbitrary group structure. The group structure should come from whatever group that actually we started with. Okay. So, there is the binary operation, for example, addition here in R2. So, when you take R2 modulo x axis, so then you want to add two cosets with respect to x axis. Okay. So, let me just do some example. For example, we already noted that. So, any coset is actually parameterized by 0 comma x plus, let us call this sorry, let me call it y1 plus x axis. So, this is one such coset here in this R2 modulo x axis. Similarly, if I take another one, it will look like 0 comma y2 plus again x axis. So, what we want to do? We want to add this. Okay, let us put in red mark. We want to add this. Somehow adding these two should correspond to y1 plus y2 0 comma y1 plus y2. Otherwise, this correspondence will be lost. Okay. The group structure on the right side cannot be carried to the left side. So, these two things somehow should match. So, we should be able to define addition here, but already we have addition in R2. So, we just use that addition and then try to actually add these two as sets and then see what happens. Okay. So, call this is some H1, this is some H2, both H1 and H2 both live inside R2. So, I can define H1 plus H2, no issue. Okay. What is this? This is just some x plus y, where x comes from H1 and y comes from H2. So, that means if you just work it out, you can see that this H1 plus H2 indeed corresponds to 0 comma y1 plus y2 plus x axis. Okay. So, let us start using group notation, then it will become actually more clear what we are talking about. Okay. So, here somehow magically this addition that we have in R2 coincides with the addition in the images. Okay. So, this is what we want to do in G mod H. So, you start with the group H, subgroup H, and then look at this left cosets G mod H, and then take two left cosets X H and then Y H, and then we can, as before, define the multiplication between them. There is no issue, because for any subsets K1, K2 of G, I can define K1 times K2. What it is? It is those product xy where x comes from K1, y from K2. So, that is not an issue, because this elements product of these elements makes sense. So, I can define k1 k2 to be the product of x y in that order, x in k1 and y in k2. So, if I do that, then what I get here, I get x h times y h will be exactly equal to x h y times h. Okay. So, note that this h y that is there in between, unless I commute these two, okay, this h y becomes y h, I will not be able to pass through. Okay. So, unless this happens, then this will not be equal to x y h h. Okay. But it is not hard to see h h will be h for any subgroup h of G. Okay. This I will leave it as exercise, verify. Okay. So, in particularly we will get, okay, this is just a question mark here whether we can commute these two. So, then we get x h y h is equal to x y h. Okay. This is only possible if we are able to actually say that this h y is same as y h. Of course, if your group is abelian, then it is always the case, but if your group is not abelian, then this may not happen. Okay. So, let us see one example where it cannot happen. Of course, whenever it happens, then we are in business, that is what this computation actually tells us. Okay. So, you can actually work out details here, but unfortunately all these examples are abelian examples. Okay. But you can still see that what computation that you are doing here. Okay. You are basically taking 0 y1 plus r e1 and then you are adding with 0 y2 plus r e2. Okay. So, then you can see that this is exactly, so these two can be interchanged. So, this is 0 y1 plus y2 plus r, sorry, this is e1, r e1 plus r e1 will be r e1. Okay. E1 is just 1 comma 0. Okay. Okay. So, here is an example. So, we do not need to actually go too much. So, even in the very first non-abelian group that we know, which is S3, this is of order 6. Okay. This is the permutation of 1, 2, 3. Then if you take for example, this subgroup which is just 1 comma 2 generated by 1 comma 2. So, which is just identity and then 1 comma 2. So, then it is not hard to see if you compute the coset 2 3 which is not same as the right coset H 2 3. Okay. So, 2 3 H is not always equal to H 2 3. The left coset and right coset, they may not be equal always. So, here we demand that it should be equal, but in this case you can see that it may not be equal in general. And in most of the non-abelian groups, okay, it is not hard to find examples of subgroups that are satisfying this kind of properties. Okay. So, what is 2 3 H? So, if you do the computation, I will just write it out. So, this is exactly 2 3 and then 1 3 2 and H 2 3 will be 2 3 and then 1 2 3, and obviously 1 3 2 and 1 2 3 they are different. Okay. So, that is why they are not equal. So, this example tells us that so the thing that we are interested in doing, okay, we want to define group structure on this G modulo H, the set of all left cosets. So, if you want to define a group structure on that, so then we may not be able to define the group structure for all subgroups of G. Okay. Then we may need to choose some very special subgroups of G only for which we will be able to define the group structure on G modulo H. And such subgroups are called normal subgroups, okay, and we will define them, and then we will see many characterizations of normal subgroups, and then using them we will define group structure on the quotients, and then we will try to study them. Okay. So, I will stop here. So, I will actually start with quotient groups and normal subgroups in the next class. Thank you.